Okay, here's our reaction, here's our example here, here's our data. The question is, you need to propose a mechanism for this reaction that fits all of our data. All right, so there's the reaction. Here is our data. What can we tell? Well, the first thing we need to be thinking about is the rate law for the overall reaction has to be the same as the rate law for an elementary step. Okay, so, overall reaction. We know the form of the rate law for the overall reaction will be rate equals K times the concentration of X3Y2 to some power X times the concentration of XY to some power Y times the concentration of Z to some power Z. All right, there's the form of the rate law. We just have to figure out what X, Y, and Z are to get the rate law for the overall reaction, and we find doubling the concentration of X3Y2 doubles the rate, which means it is first order, X equals 1, first order in X3Y2. Tripling the concentration of XY has no effect on rate. So changing XY, tripling it, has no effect on rate. That tells us that Y equals 0. So Y is a 0 here. The rate does not depend on XY. Quadrupling the concentration of Z quadruples the rate. That means Z equals 1. It is first order in Z. This now gives us the rate law for the overall reaction. Rate equals K times the concentration of X3Y2 times the concentration of Z. There is our rate law for our overall reaction due to that our data gives us. All right, now we have to propose a mechanism. And what will I be looking for when I'm looking at your mechanisms that you are proposing? Well, here's the deal. What we need to see is, since this is the mechanism, or this is the rate law for the overall reaction, we know that our slow step has to be X3Y2 plus Z goes to something. We know that that's what our first step entails. Our slow step, X3Y2 plus Z, has to go to something. So that's the first thing we need to look at. Do you have that in there? Do you have the one step having X3Y2 Y2 plus Z going to something? Because those are the reactants in the slow step. The next thing I'm going to look for is, when you come up with your mechanism, does it work out to be the overall reaction? Can I add up all your elementary steps and get the overall reaction? And then we must look at, does it make sense? Or, is the whole thing a bunch of nonsense? You didn't do things right. But those are what we're going to be looking for, so let's look at this. X3Y2 goes to something. Question, what can X3Y2 go to? And the first thing I would look at is, well, is there any way to make any of the products here? And you say, well, actually, yeah, I can make the products, because I know one of my products is X2Y2. And I can make that. I can just put an X2Y2 here, and now I've got an extra X, and I've got Z, so let's say that's X2Y2 plus XZ. That looks good. Note, there is no XZ, so that's an intermediate. So what should I do in the next reaction? Well, let's just react XZ with something. Let's get rid of that intermediate. Well, what will XZ react with? Whoa, check this out. I have not used XY yet. I've used my X3Y2 here. I've used my Z here. I know when I add it up, I must have XY over on this side. So let's just put XY in there. And what are the products here? Oh, check it out. I've got two X's and a Y. I can make my other product X2Y, and I get Z back again. By the way, what do we call Z? Right, It's the catalyst, because we put it in here and we get it out at the end. Z is a catalyst. What do we call XZ here? Right, that's an intermediate because it was made in a reaction and then used up in a subsequent reaction. Check it out. A catalyst is a reactant in one reaction and then a product in a following reaction. An intermediate is a product of a reaction and then a reactant in a following reaction. Note, if I add all of these up, which just means cross out my intermediates, I get x3y2 plus xy plus z goes to x2y2 plus x2y plus z. I get my overall reaction. A, everything is wonderful, the world makes sense. But then some of you are saying, but wait a minute. Let's look at that first step here. Couldn't I have done this? x3y2 plus z makes the other product x2y plus, okay, what do I have left in there? Oh, I've got x2y, I've got an x, I've got an extra y, plus xyz. Couldn't I have done that? The answer is yes, you could have. But if you did that, what would you next do? Well, I know x2y is one of my products here. xyz has got to be an intermediate, so I'm going to try to get rid of it next. xyz go plus has, well, what are we going to react that with? Well, we haven't used our xy yet, so let's put in xy here. And what would that go to? Oh, I can make my x2y2 now, because I've got two x's and two y's. x2y2 plus z. And when I add up these, okay, I've got this intermediate. I got my x3y2 plus xy plus z goes to x2y2 plus x2y plus z. So, note, these are two different mechanisms here. This one says we make x2y2 in the first step. This one says no, we make x2y in the first step. Which one's right? The answer is we don't know at this point. We don't have enough information to figure out which one is right. And note, heck, maybe you're feeling a little crazy and you're saying, you know, I think it goes a completely different way. What if you did this? What if, note, it still has to have x3y2 plus z goes to something. That has to be in there because that is the rate law for the overall reaction, which means one of our steps has to have x3y2 plus z goes to something. But what if you had to go to, say, xy2 plus x2z. Yeah, I still have three x's, 1, 2, 3, two y's. And what if you had that? You didn't make any of our products yet. Well, what can we do? Well, let's see. We've made an intermediate, so let's just take one of these intermediates, say the x2z plus, oh, we gotta have in our xy, plus xy goes to, well, let's make a product now, x2y plus xz. I got 1, 2, 3 x's, 1, 2, 3, the check, 1y, 1y, 1z. But still I've got a new intermediate, xz, I've got to get rid of it. xz plus, oh, I still got this intermediate up here, my xy2 plus xy2 goes to, oh, check it out, now I can make x2y2 plus z. And when I add all this together, okay, let's see, I've got my z's there, I've got my xy2, or xy2, that cancels out here, I got x2z, cancels out there, I've got xz, cancels out there. I still have x3y2 plus xy plus z goes to x2y2 plus x2y plus z. That will also work. There's another possible mechanism. crazy. Well, let's just go even crazier. Check this out. How about x3y2 plus z goes to xy2 plus x2z, our same first step, but then our next step, xy2 plus x2z plus xy. I took this intermediate and then added this intermediate to it, and then added xy, our other reactant that we have to put in there, and just say all that goes to x2y2 plus x2y plus z, our product. These two cancel, and we've got our overall reaction there. Whew. Okay, we have 4 mechanisms. I bet you could come up with even more. Which one is right? The answer is, at this point, we don't know. However, we can make a few certain educated, not guesses, but educated decisions about which is a better mechanism, which is a not good mechanism. And let's start with good education based on good scientific knowledge here. We can say right now that this mechanism, the last one we did, is probably not a good mechanism. And the question is, why is this not a good mechanism? What is wrong with this one? Well, here's the deal. Remember, each of these are elementary steps, which tells us what hits what when. This mechanism tells us that this molecule here smacks into Z. X3Y2 smacks into a Z. So we've got two things coming together. We've got our X3Y2, we've got our Z, boom, they smack into each other. Note, two things hitting each other happens all the time. Throughout these, I have these two things hit each other, these two things, all these reactions, two things smack into each other, and two things are always smacking into each other. That's not a problem. The problem is, let's look at this next step down here. When this is an elementary step, this means this and this and this must all smack into each other at the exact same time. All three of these must come together at once. Note, what if this one smacked into this one and a microsecond later XY came in? No, then that would be two different reactions. This hit this to form something, then XY hit the product. When you write this, that means something crazy where you've got X2Y, or XY2 right here, X2Z here, and let's say this is XY right here, and all three of them was bam, hit at the exact same time. All three of them was boom, right at the exact same time. Note, two things hitting each other at the same time happens all the time. Anytime two things hit each other, they hit each other at the exact same time. Three things hitting each other at the exact same time is rare. It can happen. There are reactions where it does occur, but three things having to hit each other at the exact same time is not very often. What happen much more often is two things hit and then that combination hits a third. This happens a lot. Well, let's do it again. That happens a lot, but this doesn't happen. Three things hitting at the exact same time is rare, which means that would be a very slow reaction. That would be termolecular. And a termolecular reaction is a very slow reaction, which meant we would expect this to be the slowest step. This would be the slow step because it's very rare to have three things hitting each other at the same time. The rate of the reaction would be very low if it depended on something that doesn't happen very often. So we'd expect this to be the slowest step, but we've already determined this is the slow step. Our rate law up here showed us that this is the slow step. So in this mechanism, you've got an extremely rare thing happening at a faster rate than something that happens more often. So this would not be a good mechanism because we would expect this to be the slow step since it's termolecular, but we know it's not. So that means this mechanism is not good. please try to avoid having three things in your elementary step as three reactants in your elementary step. That's just not good. All right. The other thing that we can look at is it's more of a philosophy, but it holds up pretty well. It's called Occam's razor, which, very important here, everything else being equal, the simplest explanation is more likely to be the right explanation. 2 points to that. The point that everyone remembers, the simplest explanation tends to be the right explanation. But there's also a point that people forget, all other things being equal. If you have absolutely no extra information, you have absolutely no extra data, then you can say the simplest answer is probably the correct answer. If you have extra data, though, then not everything else is equal. It could be that the more complicated answer is the right one. But in the absence of data, we go with the simple. Meaning, what's easier to get a reaction done in 2 steps or 1 step? Or 2 steps or 3 steps? What is more simple? Occam's razor says this reaction happens in 2 steps and every reaction is bimolecular, which is very common. 2 steps, bimolecular. 3 steps. This is a more complicated reaction. So if we had no other data at all, we could say, yes, this is a possibility, this is a possibility, this is less likely because it's more complicated. So these two are more likely and this is not likely at all. We can't completely rule it out, but we say this is not a very good mechanism. I doubt this is the right mechanism. This is probably not the right mechanism because it is more complicated than these two here. Whoa. So, question. Then how do we figure out which is the right mechanism in the lab? What can we do to figure out the right mechanism? Answer, look for the intermediates. What if you ran the reaction and you found, okay, as I'm running the reaction, I find the intermediate XY2 exists. As the reaction is running, I find evidence for the presence of the compound XY2. Note, this mechanism here had XY2 in it, and we found through experiment that XY2 exists in the reaction. This reaction does not have XY2 in it, does not have that intermediate, so that would tell us this reaction is not possible because this reaction does not make XY2, but we saw XY2 exist during the reaction. It didn't exist at the beginning, it didn't exist at the end, but while the reaction was happening, we found XY2 was present. So, or XYZ, excuse me, XYZ. XYZ is present, so that means this is a better mechanism. This doesn't have it, so we can count that one out. This also does not have XYZ as a mechanism, so we can count that one out, or XYZ as an intermediate. This doesn't have XYZ as an intermediate. So if we find that XYZ exists, that tells us this is the best mechanism. These three do not exist because these do not have XYZ as the intermediate. Okay. So that's nice. What if we ran our reaction and find, guess what? There's no XYZ, but we find XZ is the intermediate. Well, there's no XZ intermediate here, so this doesn't work. We've already said this probably isn't going to work, and there's no XZ here. We find XZ here, but we also find XZ as an intermediate here, which means these two are possible. These two are not possible. If XZ is an intermediate, it's found here, so that means these two mechanisms are possible. XZ is not found here and here. These two are not possible. However, Occam's razor says this is more complicated than that, so we would assume this is the better mechanism. We can't say it's not this. We can only say that this is the better mechanism. They both have the XZ intermediate, so this is a better mechanism. Since it's simpler, this is not as good a mechanism. But we can't count it out. Now, so if we can't count it out, what would you look for? What would you try to find to show that this is not the right mechanism? The answer is try to find some of the other intermediates. Try to find XY2. Try to find x2z, because xy2 is not in here, is not an intermediate in this reaction. xz2 is not an intermediate. Look for those two. What happens if you try to find xy2, try to find x2z, and you cannot find either of those intermediates? Unfortunately, the only thing we can say at that point is, since we could not find these two intermediates, this is most likely the mechanism. However, we cannot completely rule this out. This mechanism down here cannot be completely ruled out. But you're saying, why can't we rule it out? We could not find xy2 and x2z, so why can't we rule it out? The answer is, just because you couldn't find it doesn't mean it's not there. Okay? Have you ever lost something? Oh no, I lost my car key. Where'd it go? I don't know. Oh, it must never have existed. No, it existed. Just because you can't find it at a certain time doesn't mean it never existed. Just because we can't find these two doesn't mean doesn't mean they didn't exist. Maybe they existed for such a tiny, tiny fragment of time that we could just never find it. We can never actually find those because they existed for 1 × 10⁻⁻15th of a second, because their reactions are so fast, because we know these reactions are much faster than this one, billions of times faster. Maybe it's a gazillion times faster reaction that got rid of these two. Therefore, there's no way to actually find their existence. We don't know. But the fact that we cannot find these two says that while we can't rule out this mechanism, it's much less likely. This is more likely the mechanism. Wow. That's a 21-minute video just to do this one problem. And that's how it is with these kinetics problems. However, note, with just the data we've seen before, knowing an overall reaction, running experiments, we can use that to figure out the best possible mechanisms of what hits what when down at that molecular level. And I think that's pretty cool.